In this video, we're going to be solving the LeetCode question, diameter of binary tree. So in order to find the diameter of a binary tree, we need to know two things. First of all, what are we going to use to measure the length? Are we going to use nodes? Are we going to use edges? Well, we're going to use edges. You can always identify the edges in any type of tree or graph diagram as the line between two nodes. Now that we know how to measure the length, what two distances are we going to measure against? Well, what we're going to do is we're going to find the longest distance between any two nodes, and that is going to be our diameter. So in this case, our longest distance is the distance between 4 and 7. And the amount of edges between the 4 and the 7 are going to equal 4. 1, 2, 3, 4. So in this scenario, our diameter is going to equal 4. So how exactly are we going to create an algorithm to do this? We're going to need to burrow down into the tree to find the diameter. So we're going to have to ask ourselves the age-old question: which type of searching algorithm are we going to use? Depth first search or breadth first search? And since we need to go down deep into the tree as quickly as we can, we're definitely going to be using depth first search. But what type of depth first search? There's many to pick from. Well, we're going to be using post-order traversal, and this type of traversal is specifically used to find the diameter. And it's used to find the diameter for a very simple reason. Whenever we perform a post-order traversal, we're going to be moving to the left tree, to the right tree, and then to the root. So notice something very important. In my tree here, I have numbers corresponding to the exact order that we're going to use in a post-order traversal. And each time we do a traversal, we're going to start at our root. We're going to navigate down to the leftist node, and we're going to go left, right, root. And then we're going to do the exact same thing till we get to the top node, left, right, root. This left to right movement is exactly why post-order traversal is great for finding the diameter. And let's just go ahead, let's go through a very quick example. To the right here, I have a template. I have a cookie cutter version of post-order DFS. And notice something very important. First, we recurse to the left, then we recurse to the right. And that's exactly what we're going to do. We're going to recurse down to the left as far as we can. And as the stack begins unwinding, what we're going to do is we're going to increment as we go up. And then we're going to go right, and we're going to do the exact same thing. We're going to recurse far down right as we possibly can. And once again, as the recursion stops, as the stack begins unwinding, we're going to go ahead and increment the number of paths it took to get to the 2. So because this is recursion, we're going to go back up from the same path that we took. And as we go up from that path, as we unwind the stack, remember, we're going to go ahead, we're going to add to our distance, we're going to increment our length. Then we're going to do the exact same thing that we did on the left side of the tree as the right side of the tree, but with one minor variation. We're going to actually zoom down to the 6. And you guessed it, once the recursion figures out that there's no children, it's going to begin recursing back up. We want to go ahead, add to our distance. And lastly, we're going to go down to our 7, recurse back up, do the same exact thing. Go ahead, add to our distance. Take the max of those two. We don't want to add both of them. We just want to add the max. And as we increment up towards the root, we're going to go ahead and add to our distance again. And once we take the max of these two and add to this single distance right here, and we do the exact same thing on the left side, we take the max of these two and add the single length that we have right here, that's where we get 4. So let's go ahead, let's hop into IntelliJ, and let's code this algorithm. So the first thing that we're going to do is we're going to create the tree node. We don't have to create the tree node, but I think it's good to create the nodes for whatever type of data structure we're using, just because it helps us see what's going on and it's good practice. So we'll go ahead. We need to make an empty constructor, and we're going to let the AI handle most of this. We also need a constructor that's going to do the val for us. So we're going to do the this.val. And then what we're going to do is we're going to assign this.val, this.left, and this.right. And that's pretty much our tree node. Pretty easy with AI. Let's go ahead, let's create our solution. We're going to create the solution file. We're going to create a new Java class, call it solution. And we're actually going to have 3 things in here. First thing is we're going to have a private member, and this is going to house a integer for the diameter. And the reason that we need to hold the diameter at the class level is because if we recurse and we just pass in that diameter or declare the diameter within it, it's going to blow it away every single time that we recurse because it is a value type, and value types are stored on the stack. And if the stack is just blowing itself away over and over again, it's going to not be there. So that was a very long-winded way of explaining that. Next thing is we're going to need to compute the longest path, and we're going to actually need to create this method, and we're going to say private void, and the AI is actually wrong on this one. We want private int longest path. So we're going to say private int longest path, and it's going to also take in a tree node. We'll go ahead, do a really quick null check, and we'll set this to 0. So we're within the longest path function. We need to find the longest path. And the way that we're going to find the longest path is, you guessed it, post-order traversal. Now, we went into pretty good depth about what post-order traversal is, but it's pretty easy to see. We're going to recurse down the left, and then we're going to recurse down the right. And this is what's going to help us obtain the maximum left and right path. That's going to be in the form of an integer, but it doesn't really explain everything. We need to also obtain the diameter, and the way that we obtain the diameter is, you guessed it, we add the left and the right path, and we compare it against the last diameter that we had before, because we're going to be recursing. But here's the final linchpin. This is what explains everything. Each time that we return, each time that we move up the stack, we're going to increment by 1. But where does this math.max come into play? Why are we taking the max of the left and the right path? If you remember back to our previous tree, let's say that we are recursing down, and in our right node here, we have an extra length. We have an extra edge. Well, that could very well be the diameter. That could be the new diameter. And if we don't take the maximum, we won't end up with the longest length, which will not be the diameter. So let's go ahead, let's go back into IntelliJ. And what I'm going to do is copy all this, get out of full screen. I'm going to put this code into LeetCode's editor. So let's go ahead, go into LeetCode. I'm going to go ahead, get rid of this method right here. I'm going to paste in this code. I'm going to move that back. Let's go ahead, hit the run button, make sure that all the test cases pass. Let's see what our submit is. Submit passes. Our time complexity is N, and our space complexity is N as well too. Congratulations, we have passed the interview. Hope that you guys enjoyed this. If you did, smash that like button, smash that subscribe button, and as always, thank you for watching.